So after the state feedback controller, we have to study the state observer. So what is the state observer? So this is another thing that we want to do with the system. So the first thing with the controller, we wanted to make the system like reach stability or go to a particular state, or like track a given trajectory. But for all those things to be done, we saw that yes, there can be a state feedback controller. There can be, of course, there can be many other controllers, but that state feedback controller is one controller that we studied in this course, which is a very fundamental understanding about the systems uh, and fundamental understanding based on which other advanced controllers are also designed. But we came to understand that to design such controllers, state feedback controllers, what we basically need is the information of all the states of the system that is required. So the information of all the states is absolutely important in designing a state feedback controller. However, we have already discussed this before, and this is very common sense, that all states may always not be the physical variables of the system, as such may not be measured, and even if they are physical variables, then also it may be possible that for some systems those variables are we cannot actually tap out those variables, we cannot actually measure those variables even though they are physical variables of the system. And sometimes the states are very like abstract quantities which are defined for the systems, because state space representations, as you know, we can move from one representation to another, and we really cannot observe, we really cannot measure these states, and many times it can happen so. But the thing that we can always measure is the output. The output remains same from the system, because it is what we obtain out of the system, that is always measurable. So there comes a problem of estimation of the states with the help of the outputs, and that is exactly what is the reconstruction property, reconstructibility property of the system we are interested in, and that is given by the observability matrix. So if the system is observable, that means we would be able to reconstruct the present state by the knowledge of the past outputs. By the knowledge of the past outputs, we would be able to reconstruct the present state information, and that information we can then use for designing the state feedback controller. So in this lecture, we would understand how we can actually observe the states or estimate the states. So it is the state estimation or state observation problem, and that we do by designing what is called the state observers. So let us look at what is a full state observer, and this is also well known. This particular observer that we are studying is well known as the Lyapunov observer, by the name of the person who first proposed this sort of observer, Lyapunov observer. This is very simple. So what we do basically, we construct, so yeah, it is already written here, Lyapunov observer. So what we do, we construct a this is a fictitious system. So this is a virtual system. This observer system that has been constructed in this equation is a virtual system, and it sits within the computer. This sits within the computer. This is not a real system. So this system sits within the computer. So you can always you are always getting the x hat states by doing some computation which is involving this state dynamics which is given in this equation. With the help of this state dynamics, we are able to calculate x hat at any point of time, and that x hat is the estimated states. This x hat is the estimated states which we estimated states, estimation of which estimation of x which is the real state, estimation of x which is the real state of the system. The real state we are unable to measure, we are able to measure only the y. With the help of this y, see in this state observer dynamics, in the state observer dynamics the y is there. In the state observer dynamics the y is there, also the u is there, the input is also fed there. So, with the help of this y we are able to get the x, we are able to get this x. That is what we are doing. Why you will say, why cannot we invert this C? Yeah, the answer is also pretty obvious, because this C is not a square matrix in general. It is not a square matrix in general, and hence you will not be able to invert this C. So you have to go via a longer route, which is designing a state observer, and then what you will actually do is design some attributes of this state observer, some parameters of this state observer, which is this particular gain L. You will design this gain L in such a way that your x hat approaches the actual states x asymptotically. This is what the goal is for any observer design. Your observed state must approach the actual state asymptotically, at least asymptotically. So that is what exactly this particular observer will do. How it is getting done, let us see. So you see here, notice that what we have done. So the construction of observer is very simple. If you notice the actual state equation, this is copied here. The first part of the observer equation is simply a copy of the actual state equation, simply replacing the state x with x hat, that is all. However, we would add always, so this is a simple linear observer. If you look at any advanced observer also, if you would come across, then also you would see that this is the philosophy employed everywhere. So first we copy the state equation replacing x with x hat, and then we add on some term. We add on some term. Here that term is this L y minus c x hat. In this Lyapunov observer, this additional term, which is the observer, it is also called the observer injection term of observer injection term is injected into the observer. Okay, so that term here is L y minus c x hat. Now c x hat is what? C x hat is the estimated output. With the help of the estimated states x hat, if you do c x hat, you will get the estimated output, and you have the measured output. So you have a difference between these two, and then you multiply with L. That forms your injection term. This L is of appropriate dimensions. Okay. Now if you do some manipulation here, what sort of manipulation? You see, L minus LC x hat is taken with A, so you get A minus LC into x hat. Bu is as it is, then Ly is there. So this Bu and Ly, these terms are known to you, because you you are supplying to the system some control input that is known to you, y, this is the output from the system that is known to you. So your system state, your observer state dynamics becomes x hat dot equals to a minus lc x hat plus bu plus ly. This is the estimation error of the output due to the observer, that is I already told about. Now our intention is to have x approach x hat or x hat approach x in asymptotically. So we need to basically make a error system here also. An error system we make defining the error as x minus x hat. Then we try to make an error system, and then what would be the intention? To stabilize the error system. If we can stabilize the error system, that would mean that the error will become 0 asymptotically, which would mean that the state will converge to the estimated state will converge to the actual state asymptotically. Then our objective is fulfilled. So if we do that system, like if we do that error system and then we take the E dot, so if E is defined like this and we then evaluate E dot, we have to find out the dynamics of the error system. E dot we are doing, so E dot you will see x dot minus x hat dot, then you put x dot and x hat dot in place of these two, then what you will see is that your this bu will cancel out and you will have this a minus lce. This is what you will get ultimately, ax minus ax hat. So ax minus x hat, and another what else you will get? You will get ly is lcx and minus lcx hat. So again lcy you will lce you will get. So ultimately you will get a minus lce. So this is a simple homogeneous system you are getting. You understand now why the study of homogeneous system was so important, because always you will get this system again and again from even non-homogeneous systems. So what you are getting is this. Now our job is to basically stabilize this system. So basically what is your objective then? Your objective is to design L in such a way that A minus LC is a stable matrix. That means it is a Hurwitz matrix, or the matrix in which all the eigenvalues are placed in the left half of the S plane. So the question now is whether we can design such an L or not. In the case where we had A minus BK and we had to design K, we found out that we can actually design K if the system pair A B is controllable. But here it is not A minus BK, it is A minus LC. The gain which is to be designed sits ahead of the system matrix C. There the gain K was sitting after the system matrix B. Here it is sitting ahead of the system matrix C. So let us see what is the condition. So this is a full state observer. So this is a condition, you see, that we can actually make a dual system of the original system. Going to the dual system is beneficial here. What is the dual system? The dual system, you know, if ABC is a system, the dual of it is A transpose, C transpose, B transpose. The states are not the same, they are different states. Okay, so these variables have been given different names. But you notice that what are the matrices here? A transpose, C transpose, B transpose. So now if the dual system, this system is completely state controllable, then we can choose a V which is acting as the input here. We can choose a V equals to minus L transpose Z. We can do that if this system is completely state controllable. We can choose a state feedback gain which I term as LT, L transpose here. We can actually do that, that is already proved, and then the closed loop system matrix will be this. This would be the closed loop system matrix, and by choosing L transpose we can get a desired set of eigenvalues. We can choose our L transpose so that we get a desired set of eigenvalues. Now there is a simple math which shows that this transpose of this closed loop matrix AT minus CTLT is basically A minus LC. This means that the eigenvalues of A transpose minus C transpose L transpose is same as the eigenvalues of A minus LC. So if you want to place the eigenvalues of A minus LC in desired locations, it is same as placing the eigenvalues of A transpose minus C transpose L transpose in desired locations. And this problem we have already solved. This problem, placing the eigenvalues of this matrix, we have already solved. We know that if A transpose and C transpose form a controllable pair, then I can design L transpose so that I can place the eigenvalues in desired locations. So that is what is stated here, the necessary sufficient condition for being able to choose the desired L. I should write L transpose, but it is fine. L transpose choosing means choosing L. So is that A transpose C transpose is controllable, which basically means AC is observable, or the observability matrix is full rank. So that is the condition. So if AC is observable, then I will be able to choose a matrix, an observer gain L, so that I can place the eigenvalues of A minus LC in desired locations. So that is fine. I have my AC observable. Now how to choose this L? How to evaluate this L? That remains the question, right? But it basically does not remain the question. How you choose the gain L is basically you go to the dual system A transpose, C transpose, B transpose, and then you choose L transpose in the same manner as you have chosen K. As you have chosen K, you choose L transpose by looking at the desired closed loop, desired characteristic polynomial. You can then choose your L transpose, and that will give you L, and that is the method basically. So all the previous methods for choosing the state feedback gain K holds here to choose the matrix L transpose. So here you choose L transpose, and what you have to do, you have to precondition your A and B, so that A and B which were there now becomes A transpose and C transpose. That is all. Now we have to verify if we have the observer in loop, we have the observer in the control loop, then also the system will remain stable. Now please bear this in mind, that the controller now which we are constructing is not using the actual state information but the estimated state information. The controller is using the estimated state information or the observed state information x hat. So u is basically kx hat here. So the question is this: it is not obvious that if I had used x, I had already proven that it would be stable. But it is not obvious that if instead of x I use x hat, then also the system will be stable. It is not obvious. So we have to prove it. So how do we prove it? We look at the closed loop dynamics, because we want to prove closed loop stability. Closed loop dynamics, we look at x dot equals to ax minus bkx hat now. So this x hat is basically x minus e, and hence we get this equation. And the observer error dynamics is there, which we already know, which is this equation. Now we combine the dynamics. Which dynamics? X hat dynamics, x dynamics and e dynamics. The actual state dynamics and the observer error dynamics we combine to give rise to this appended system. This system with appended states like this. And this is basically this thing. So why did we go for this e dynamics? Because a e variable is coming here, so we also check the e dynamics. Now we are getting, with the appended state, we are getting this as the total observer in loop system. This is the observer in loop dynamics. Looking at the observer in loop dynamics, it is very obvious that the characteristic equation would be this. And here in the characteristic equation, it is very clear that the eigenvalues of a minus bk and a minus lc remain separated from each other. They do not get intermixed with each other. That means the total eigenvalues of the characteristic equation of that complete closed loop dynamics or the observer in loop dynamics is the eigenvalues of a minus bk and eigenvalues of a minus lc separately taken together. And separately, since they are already stable eigenvalues, the total characteristic equation will also have all stable eigenvalues. So this shows that the controller and the observer independently contribute to the stability of the overall system. They independently contribute. There is no intermixing of the eigenvalues. There is one eigenvalue does not influence the other eigenvalue. The eigenvalues remain separated. So since both these systems, smaller subsystems, are stable, the entire observer in loop system is also stable. What is the block diagram of the observer in loop? It is like this. So you have the plant here, which is whose model you have given as ABC. Now you have this Y coming out. With the help of the Y, you are constructing. So here is the observer. You are constructing x hat, and you are also, okay, let us take this x hat and make, let us take this x hat and make a controller here. So let us have a state feedback controller, which is now getting constructed using x hat. Okay, so let me have a double arrow here just to denote that x is not a scalar. Okay, and from the state feedback controller I am getting a u which I am supplying to the plant. This u I am also feeding to the observer. This u I am supplying to the plant. Inside the plant, that total ABC system is there. Okay, so this is how the block diagram looks like. Now There is also a concept of reduced order observer. Why this concept is coming? Because many times you will find that the output forms a particular subset of the total number of states defined in the system. The output forms a subset of the total number of states in the system. The outputs are exactly some of the states. This is what I mean. The outputs are exactly some of the states. So let us consider that outputs are the first R number of states. This x1 in R dimensional state space. C is IR. I should not write I should write actually like this. This is the denotation 1R. So there are R number of ones here, and then remaining are 0. Remaining n minus R are 0. That means that output is basically formed with the sorry, this is IR only. This is IR only, because this is like this. Y is equals to your x1 up to xr. This is like this. So your x1 to xr, all these are your outputs. All these are your outputs. So now actually I have divided the entire states into these two blocks. One is x1, another is x2, and this x1 is in R to the like Rth dimensional real state space. So C is IR 0, and so this means that this x1 is basically the output. X1 is basically the output. So it is not required to estimate x1, because you are measuring x1 anyway. You are measuring x1 anyway, so it is not required to estimate x1. However, please note that if you have a noisy measurement, or if there is disturbance in the output, then it is best to go with a full state observer, because in that case the output measurement may be faulty or not trustworthy. But if you have a very trustworthy measurement of the output, then you can go for the reduced order observer. Here the computation basically becomes a bit lesser, that is all. So what is the reduced order observer then? Then in this case you need to only estimate the remaining states. So you define the estimated states as x2 hat in this manner, Ly plus z, and you construct the z dynamics. Z dynamics you construct in this manner, a hat z plus g y plus hu. So some a hat into z, some matrix coefficient which has to come with the output. You have to feed the output here, you have to feed the input here. So these matrix coefficients are through which you are feeding the input and the output to the z dot dynamics. The error is only this much, and then you calculate what is the error dynamics, E2 dot. E2 dot, if you calculate, you will get this equation. This is a bit lengthy equation. If you evaluate E2 dot, you will get this equation. There can have to be some rearrangement of terms, and one has to note that x1 is basically y. So you have to keep in mind while evaluating this equation that x1 is equals to y. When you arrive at this equation, then your intention will be basically to zero these coefficients. These coefficients you want to make 0. How you do that? You have this h and g to choose. You see, you choose h in such a way that this becomes 0. you choose G in such a way that this coefficient becomes 0 identically. Then you have your A hat. This A hat also you can choose in such a way that this becomes 0 identity. Now what the equation remains is basically E2 dot equals to A hat E2. That is what remains. This is only remaining term. And A hat is A22 minus L A12. This is same as A minus LC form. So in place of A, now you have A22, in place of C you have A12. So if A22 A12 pair is controllable, is observable, then you would be able to select your L as per previous procedure by going to the dual system. And it can be noted, so this is a statement without a proof coming, that if you have your AC as an observable pair, then a system of this form, of this particular form, where you have the output as a set of states, that is you have this form of C. If you have this form of C and then you break the system into x1 and x2, you will get these matrices A11, A12, A21, A22. In that system, the pair A22, A12 will also be observable pair. So this statement comes without proof. However, there is a proof, so this statement is genuine. So in this sort of a system representation where x1 is the output, basically x1 is basically the output, then that A12 and that A22, this A22 A12 will form a observable pair. That means you will be able to basically design the L. So with this, the lecture on observers complete for the purpose of this course. So in this course, for LTI systems, you had only the state feedback controller, the very basic one, and the very basic observers, the full order and the reduced order observers. These are just meant for introduction to controllers and observers. There are of course a vast variety of other advanced controllers and observers, because there are many limitations of these basic controllers and observers, but we will not go into those discussions. Only for those who want to pursue higher studies or deeper studies in controllers and observers or in control systems, they can take further courses in your higher classes, and you will be able to study all those different controllers and observers which are out there. Okay, but all of them rest upon this idea, the idea that we talked about, that we have to place the poles, place the eigenvalues in the left half plane. When can we do that? Okay, the idea of dual system, the idea of how we are constructing the observer as a copy of the original system, adding with some injection term. These ideas will remain the almost same even in advanced controllers and observers. So with that, I end the discussion. Yeah, one thing before ending the discussion, let me point out that you can actually, you can always come to this form. This is a specific form. I hope you have understood. Your particular system may not be in this form, where your some set of your states is basically the output, or your C matrix is basically in this form. It might not happen so. It might not happen so. But you can always come to this sort of form by using some similarity transformation, and that similarity transformation you can evaluate. You can try to evaluate at least for a scalar output. Suppose your y is simply x1, which is a scalar here, then your c, what you intend is this, right? So you try to evaluate what your p would be, so that you can come to this sort of a c, this sort of a c, then your job is done. So that means whatever this c2, whatever your c1 is, your c1p is c2. You try to get a p which is non-singular, so that your c2 comes in this manner. Try to solve this problem, and I will also give you a hint in another way. If you look at the controller canonical form, you will be able to appreciate that this C2 is basically the B controller canonical form transpose of that. So with that hint also you may try to work in some way. So with that I will leave you, and thank you for your attention.